All right, welcome to Earth Science, everybody. How we doing? Time for sedimentary rock. So you're going to go down to page 7 of that big note packet. Again, the links will be there if you're on the survival guides. This is all of the rock stuff. So get yourself right to page 7, and let's talk sedimentary. Our second of 3 rock types. You should have already done the basic rock cycle, which is this diagram, although this one's missing its bottom half. You should have already done all of the igneous stuff. And now we'll do sedimentary, and then next we'll move into metamorphic. All right, so sedimentary rocks, which are great. Maybe they're my favorites. What they are rocks that are formed by, I don't know, maybe an accumulation of material at Earth's, I don't really love how I wrote this, at Earth's surface. So, I mean, we'll talk about it here, and we talked about it on the diagram in the rock cycle thing, but if you take a bunch of material or sediment and you put it all in a big pile, in some cases, if that pile keeps on getting piled on and keeps on getting piled on and keeps on piled on, that can lithify into sedimentary rock. All right, usually within bodies of water tends to be the most common depositional environment, not the only one, but the most common. This material or sediment gets buried. Can you guys see this? We'll go a little bigger. The sediment gets buried and then goes through this, here's this $10 word, lithification. All right. Lithification is really what your reference table shows you right here. I'm not sure. I guess I should search. I'm not sure that that word itself would be super critical on a regions type situation. What they're more likely to go with is, how does sediment turn into sedimentary rock? Well, yes, lithification is the thing. But if you want, like, what does that mean? It's because those sediments go through deposition, that drop off accumulation of sediment, burial, we know what that is, compaction, they get squished because the more that's on top, the more weight, the more pressure, and then cementation. Mineral cements can help stick those grains of sediment together, giving you a sedimentary rock. Any of the other 3 types of rock can turn to sediments. So you take a metamorphic, you take an igneous, or you take a different sedimentary, and you put them somewhere at Earth's surface through the process of weathering, erosion, which is like what we did for weeks in the first part of this marking period. Let's talk about how Earth's surface gets beaten up. Now those sediments that process creates can turn into sedimentary rock, which is what we're going to say right here. Sedimentary rocks can form from these sediments. Okay, so that's kind of wordy, but don't let it get more complicated than it needs to be. Take a pile of sediment, sand, put it under some pressure, it can turn into a sedimentary rock, which we're going to call sandstone. Easy peasy. Okay, there's 3 basic types. I think what we'll do, I've got little sections for each one of them. Maybe let's chuck a couple notes on here, and then we'll say, okay, here's what clastics are. So we'll come back up to this section a few times. Let's start with clastics. This is going to be old news. In fact, this is going to be almost exactly what you guys did on that other sheet. Take exposed land surface. A classic sedimentary rock is like your, I almost want to say classic. Clastics are classic. They're like the easy to picture exact version of a sedimentary rock that, if you're tuning in here, is probably what's in your head. Take exposed earth, put it through weathering, create sediments. And we can say, then those things flow into a river, which is red today for some reason. Erosion moves sediments. That's generally wind and water are the big sediment movers here on this planet. And eventually, what's going to happen is that those dump out into depositional basins. And again, most of the time, those are underwater. Doesn't have to be, but a lot of time it is. Oh, that's an awful line. But you guys have already done this once if you've made it this far. So sediment, 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 sediment. And if you're down here, you're getting smushed. So like this diagram shows us, take individual mineral grains, all those minerals that came out of those rocks that existed up here. Now they're broken down into sands. Just picture the beach. And put more pressure on them so that you're reducing the pore space and squishing them together. And then as that groundwater gets squeezed out of them, if there's anything dissolved in that water, it can act as a mineral cement to essentially glue together that rock. So clastic rocks are the ones that are just literally made from other bits of rock, made from actual, that's not how you spell that, ACTUL, made from actual sediments. So bits of other rock, which is going to be one of the things you look for. Now, your rock lab, your drawer of rocks looks like this. Some you're going to be able to see. Like, look at that, number 2. You can see those. Those are bits of other rock. So can you picture the history of this rock? At some point, all of these other rocks ended up in a pile. This kind of looks like concrete almost, but natural. They all ended up in a pile. They got cemented together. There you go. Or this guy that I say is gritty. And this is what the lab's going to be. I'm going to give you some very strong hints. The lab's going to be easy. Don't panic about it. But if you can feel the grit that's in it, that's probably a clastic sedimentary rock, which, since you're sitting here on a computer screen, probably frustrated that you're watching yet another YouTube video, you can't feel that rock, right? Unfortunately. So we'll make do. I'll make the lab easy on you. But I guess with all that babbling, clastic sedimentary rocks are really literally made from bits of other rock. All right. How about chemical? This process could look just like clastic. And so the clastic, I think, is easy to picture. Like if you've seen the Salmon River on like high water days or in the spring when it looks kind of brown and muddy, you can picture what sediment in a river is like. You guys already know that. And it washes out and goes somewhere and eventually lands somewhere. What we're going to do now is make a switch in our head to say that exact thing happens, only instead of a physical bit of sand or silt or clay floating in it, what if it's an ion, I-O-N-S? What ions are, if you take something, the easiest to picture, and one that in fact we've already done in this class, is if you take sodium chloride, which is salt, and you put it into water and you dissolve it, you separate those sodium and chloride into ions. When you get to chemistry, you're going to learn a lot about the type of bonds that is and how likely it is to dissolve, and solubility curves and all that fun stuff. For us, all we're going to say is, picture Kool-Aid. I've made Kool-Aid. Dump the sugar into the thing, stir it up, the sugar dissolves, right? So that's a sugar solution. Salt water is a salt solution. It's just water with the sodium and chloride from the salt dissolved into it. So if the Salmon River flows over any type of rock that is at all soluble, and there's a lot of it out there, the ions enter into the stream. And really, so the Salmon River, you can say, but it's not salt water. I'll say, no, it's not, but it is a little tiny bit. There is a tiny bit of sodium and chloride in there. Now, eventually take all that water and flow it out to the ocean where it stops. Yes, that's where the salt water really builds up, because then the fresh water evaporates, comes back into the sky, dumps down as clouds, picks up a tiny bit more salt, and does this over and over and over again. So the ocean, being the end point of that, stays salty. A good question, and one I won't answer today, if you're being clever. Shouldn't the ocean get saltier and saltier through time then? I won't answer. We'll have to think. So ions move in a stream, like, rather than sediments. All right, so let's draw our river again. I won't make it like a river of blood this time. That was disturbing. We'll use purplish blue. Here's our river. Now, instead of weathering, erosion, and deposition, we'll have, okay, still weathering because it's dissolving. But we'll just say that. We'll shortcut. Dissolved solids go into solution. Again, don't let that word panic you. Solution is just, Kool-Aid is a sugar solution. Salt water is a salt solution. It's just those ions in water, okay? So dissolved solids go into solution. They come down here, and what happens is that water evaporates. Salt doesn't join that trip. The salt's got to stay there. So here's the reason why back when we did the weathering lab, if you remember, if you did that lab, hopefully you did, I took some of the salt water, and there's still some water in there. I took some of the salt water from the first several trials, and I dumped them into this beaker. This is the actual beaker. It's been sitting in the front of the room if you're here. And what has happened, it looks like the water probably started right about there when we started this experiment. What has happened is that water evaporates, but the salt gets left behind. I can't dump too far because I don't want to dump it all over my computer. But you can see it's forming these salt crystals. Those salt crystals would be considered a sedimentary rock, a chemical sedimentary rock. And if you were really doing a good job on that thing where you had to scramble and try to find all the words, this would be called a precipitate from solution. That's the fancy, heavy, scary word for this. A precipitate from solution. Us, it's just rock salt. This was salt water. Water's gone. Now it's rock salt. Sometimes I say, because everybody knows what dissolves is. You know what it means to dissolve. You saw salt dissolve. You put some salt in some water and it dissolves. Sometimes I say this is like undissolve. That's not a word, so we really shouldn't use it. But this, I think it helps illustrate it, right? It makes it kind of obvious, hopefully. So we get I'm going to write it. This is going to be a complicated, word. Let's make it bigger so you can see the spelling. So we get a chemical sedimentary, which is a precipitate. Where's it start on that line? Precipitate from solution. And again, don't let that intimidate you. That's very chewy vocabulary. But you take salt water and evaporate it, and you get salt. You just separate, that process. So let's go back up and define here, just so we have it in our notes for everybody that goes back and reads their notes and studies. This is made from evaporated water. Whatever was in that water when it evaporates will be left behind. In fact, let's hit pause. Let me find a picture I took over in Mr. Archer's room. So if you've ever poured a Kool-Aid or a soda or something like that into a cup, not finished it, but left the cup sitting there, you get a situation that's like this. I found this over in Mr. Archer's room. It's a coffee. Somebody poured a coffee. It got down to there, and then they left it sitting somewhere for a long time, and the water's all evaporated, but whatever is in the coffee that they're drinking formed this kind of crust on the outside because the stuff in a solution doesn't evaporate with the water. The water evaporates on its own, leaving behind whatever's there. So you do this with Kool-Aid and you get that like little blob of red at the bottom of your cup if you leave it there. That's it. That's really a kind of a chemical sedimentary rock. It's that same exact process. Okay. Yeah, sound good? All right, last one, organic. Now, this is going to be kind of an example of bad teaching. Not that any of this YouTube teaching is great. But listen, our one organic rock you're going to deal with is coal. And it's really like this lab is a lot harder to give you a method. When he did igneous, I could say, okay, do dark versus light, then do coarse versus fine, throw it on the table, and you got that. That's like steps. Do this, do this, do this. The next two labs are more like make some observations, see what you think, see if anything rings a bell or fits in this category, and then investigate and think and observe. It's not as like linear with the procedure, unfortunately. And when it comes to coal, it's kind of the hardest, most difficult, because it really looks a lot different than the other sedimentary rocks. And if you could feel it, you guys would feel how it's very light. And you could just kind of, like, once you know what it is, you know what it is. And you wouldn't confuse it with other ones. But the properties of it are kind of hard to nail down. In this one, it's a good picture. You can see some of the layers that are there that would have formed. It's kind of like the sedimentary process with sand, only if we did that sedimentary process with layers and layers and layers of dead plants instead. If you've ever been to a peat bog of any type, a kind of a swamp of any type, where trees, plants grow and die and grow and die and grow and die, and especially in water, if it just happens in the woods, they tend to kind of rot and fall apart. But if it happens in water, they can preserve, and all of that carbon that's in there can stay. Like in Ireland, there's peat cutters. It's like this swamps that dried out. They'll cut those layers and get kind of this really dense. It's a soil still. It's not coal, but you get this kind of dense, rich log of kind of earthy, peaty, heavy, wet material. But you can burn it. It'll burn. It's not super efficient, but it'll burn. Take that and put it through more pressure and more pressure and more pressure. And in fact, we're going to talk about this as a sedimentary form of coal, and then you put that under a ridiculous amount of pressure, under like a forming mountain, just getting the Jesus squeezed out of it, then you're going to form a really hard type of coal too. So coal's going to show up a couple times. It's difficult to say, like, here's where this fits into your process in the lab of figuring out what's what, but it's very easy to say, this is what coal is. You'll see it. You know what it's like. So we are made from organic processes, hydrocarbons. That's the whole thing here. So the sunlight hits a plant leaf, does that whole photosynthesis thing that Hefty taught you about last year. That forms plant tissue with carbon and hydrogen bonds, stuff that Nyland will teach you about next year. You take those hydrogen carbon bonds, that's like molecular locked up energy, and that's what, if you set something on fire, you're releasing that energy that's in that. It's difficult. It's a difficult concept, but it's like photosynthesis stores the energy in the tree through plant tissue made of hydrocarbons, and then we can exploit that, right? So take layer upon layer upon layer upon layer of it, build it up, you got yourself coal. That's about it. All right, so that's really, where are we? That's really it for organic. And that's going to be the only one that's on there. Made from plants remains. Cool? All right, what's next? Oh, yeah, so then, of course, there's always one that's going to monkey with things. We have our friend... I don't know if I meant to say calcite here, I meant to say limestone here, but limestone, yeah, I meant to say limestone. Limestone is here to confuse things. Limestone you can get really almost in all three forms. Limestone can build up with like shell remains. So that feels like, geez, that should be an organic rock. Limestone can form chemically from a precipitate. So you feel like, oh, that should be a chemical rock. Limestone can form from the accumulation of certain sediments that are laden with that kind of stuff. So you might say, well, that should be a clastic rock. So limestone is is the screwball. It can fit in all three categories. So what do? The good news, that's the bad news. The good news is in its composition. Its composition is calcites. Now here's where we would have benefited if we did minerals first. We're doing minerals last. On the back of the reference tables is the minerals guide. And on that, there is a mineral called calcite. You'll see it eventually. Don't panic about it just yet. And then if you come over here to characteristics, it says that it bubbles with acid. So if you take a rock and you've got a little acid bottle, hydrochloric acid, and again, if we were in class, I would do this for everybody. You squeeze it on there, it just fizzes a little bit. It looks like Sprite. It's nothing like super dramatic and exciting. It fizzes a little bit. All right, because of the calcite being in it. So it's like, well, this one's a nightmare because it could look like anything. I could give you 10 different rocks and say, good luck identifying these, and it could be limestone, 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 right? If you dump acid on there, you see bubbles, it's limestone, period, job done. Okay? So there are forms of limestone that can fit into all three categories. Luckily, they contain, we already said this, I mean, just writing that down. If you miss that sentence, I'm not worried about it. All right, there's our reference table. So when it's time for the lab, again, I can't really give you a method of, okay, first, is it light or dark? In fact, I don't want to see color on this lab at all. And I say that in the lab. I wrote, don't write color here, period. And then I say, except for coal. You can tell me the coal one's black because you see the black one that's kind of shiny and kind of layery, and boom, you're done, coal. For all of the other ones, there's 9 other rocks in the lab. Don't tell me the color. It doesn't matter. You can go to this beach here and get that kind of brown, I guess we'd call it sandy colored sand, right? Go to a beach on the Gulf Coast of Florida, and it's like white sand. Go to a beach on like a volcanic island, Hawaii, Iceland, you can get black sand. So I could give you a white sandstone, a black sandstone, a tan sandstone, a pinkish sandstone. Color doesn't make any difference. You know what makes sandstone sandstone? It's made of sand, and that's it. So that's all that, like the thing you got to observe is more like the composition, the makeup of the rock, which I know can be like difficult and intimidating, but you guys are smart folks. You're going to figure it out, no problem. All right. How's this thing organized? We got our class sticks up top. Remember, those are ones that are made of bits. And in case you forget, look, this is going to tell you right here. This one's made out of bits. This one's made out of bits. This one's made out of bits. And this one's made out of bits. So you got sand making sandstone. You got silt making siltstone. You got clay making shale, not claystone, unfortunately. And then you got this guy here. This is a little confusing. What if you have boulders, cobbles, everything basically. This is like the kitchen sink. You got all the bits, all mixed up and mashed up. That will give you one of these two rocks. If they're rounded off, we say conglomerate. If they're angular, we call it breccia. Because of the nature of this year, not everybody did the glacier stuff. One of the lessons in there is that glacial deposits, and this could be huge if you have to do a regions. Glacial deposits are unsorted. So a glacial deposit that turned into a rock would probably more likely be one of these guys, versus river and wind deposits are very sorted. They're organized. You go to the beach, you only see sand. Lake Ontario has done a fantastic job with the wind and waves of organizing those particles. It's a heavy job. If I gave you a whole bunch of stuff and said, all right, organize these by pebbles, sand, silt, and clay, and you're like, 1, 2, forget about it, right? That natural process of deposition with those sorts out those materials. Running water sorts stuff, okay? And that's really what you're going to have to look for in the lab is what do I see here and where does it fit? I wish they said chemical there. They say crystalline, which is not just plain not the right word in my book. So I'd like you to please still with me. Word chemical right in there. That's what we really mean here. One thing that's very nice is that they say, and again, you should have found this word if you did the previous work. These are evaporites. Evaporites form from evaporation. A precipitate, that's that word we put up there, is the same deal. That's the precipitate from solution. That's the rock that forms from that evaporation. And that's where the vocab here can be like scary. If I handed out all this stuff and put them on cards and we all had to memorize a ton of vocab, it'd be intimidating. But really, it's going to be more about, oh, there's a question with that evaporites word. I know then we're probably talking about one of these three rocks. And there's going to be the key to nailing this test. Again, this test is very 100-able. And you could almost, if you're clever, not do any of this rock stuff if you're really patient and you find the question says something about evaporites and your choices maybe go with the composition then, or at least, I mean, there's only 3 of these. If there's 4 choices, one's out the window right away, right? We know it's not shale, so this is about not necessarily memorizing every vocab word, but being ready to go to all these charts and find all that vocab and then just figure out what they're trying to ask you, which is why I had you do that assignment with the coloring of the different things, finding words. I was accused of being evil. You know who you are. You sit right over there. But it was deliberate. It was for a reason. All right, what else we got? Then we got our friend Limestone. Again, what a mess. This thing could be its own whole reference table, but calcite's the giveaway. And then coal. You got coal. It's coal. Try these. I think the way that this unit's starting to go, I'm not sure I'm going to end up using these as a quiz. Like I said, I might. That when I numbered them all, I said maybe I'll try to use them. Maybe we will towards the end. But this could be like hey, I should practice this on my own and figure it out. Give them a go. See what you think. And it'll get you just banging around the reference table a little bit. Having some fun. You'll do great. So then when it's lab time, I'll do a separate video, just introduce the lab. But here we go. Hey, look at that one. That should look familiar. That's actually last year's experiment, but same deal. And there's just places where I had to really give hints, and I'll help you out on the lab in the video to explain what I mean by those. Or these ones I just put the answers, because it's like you really can't. I mean, you can't with a picture do some of this stuff. So in sympathy with what you're trying to fight through with these labs. Number 9 is dolostone. Number 10 is gypsum. We better not screw those ones up, boy. All right, that's enough babbling. Happy St. Patrick's Day, even though you're not watching this on St. Patrick's Day. I wish you well. Take care, everybody.